YouTube channel Chemistry for Neet. Yesterday we have we had a live class where I discussed the mechanism of different electrophilic substitution reaction like Friedel-Crafts alkylation, acylation, and nitration reaction. Today I am going to discuss the orientation of the substituents that are present already in the benzene ring. Just let us consider the reactions. If we make a nitration reaction of benzene, that is benzene, and you are giving a mixture of concentrate nitric acid and sulfuric acid at a temperature of 50 to 60 degrees centigrade, then you will get nitrobenzene. Okay, here the reaction mixture, the electrophile, the substituent electrophile produced is nitronium ion, that is NO2 plus ion, and which actually replaces the hydrogen, one of the hydrogen of benzene ring. Now what happens if we further nitrate the nitrobenzene? That is, here the starting material is nitrobenzene and you are maintaining all the conditions, that is you are giving a mixture of concentrated nitric acid, a mixture of concentrated nitric acid and sulfuric acid, and maintaining a temperature of 50 to 60 degrees centigrade. Then what happens? The same reagents are also given here and the product so formed is NO2 already present there, and the other nitronium ion comes in the meta positions with respect to the substituent NO2 present in that positions. Okay, so this position is called meta, this one is ortho, and this one is para. So here the compound form is meta dinitrobenzene. Meta dinitrobenzene. Okay, now if we nitrate toluene, that is the starting material is toluene, and you are giving the same reagents, that is a mixture of concentrated nitric acid and sulfuric acid, and maintaining a temperature of 60 degrees centigrade, then the product formed is a mixture of orthonitrotoluene and para-nitrotoluene. That is a mixture of, here the C is already present, the NO2, the reagents NO2 comes in ortho position as well as in para position. That is why we get a mixture of orthonitrotoluene and para-nitrotoluene. Now why is that happens? So the substituent already present, actually that depends upon the orientation of the substituent already present in the benzene ring. That substituent actually direct the incoming electrophile where to come. That is, in case of CH3, we are seeing that CH3 has the orientation of ortho and para, but NO2 has the orientation of meta. Now why that happens? To understand this, we need to do some work. That is, let's do some electrophilic substitution of benzene, and that is the electrophile E plus. Okay, now here why is the substituent already present in the benzene ring? Now if electrophile comes in ortho position, that bond has to be broken and the positive charge resides on that carbon which is carrying the substituent Y. Okay, so that happens. So E goes to the above the plane, and the hydrogen that was already present in the benzene ring goes to the below the plane positions, and those two pi bonds remain intact. Now we have to make some resonating structures. We have to make some resonance structure of this. Okay, so the what be the resonating structures of this carbocation? First of all, this pi bond that will be moved towards this bond, and the pi bond is breaking from this carbon, so a positive charge will be here. Okay, so the resonating structure will be the Y substituent already present, the E remains in above the plane, hydrogen below the plane, that pi bonds remain intact, and the pi bond shifts from this bond to here to there. So a double bond comes here, and the pi bond is broken from this carbon, so the positive charge will be on this carbon. Okay, so that will be one of the resonating structure. Then what will be the next resonating structure? This pi bond will come here to neutralize this carbon. That positive charge of this carbon will be reduced, will be neutralized, but since the bond is broken from this carbon, so the positive charge will be shifted from here to this carbon. Okay, so the next resonating structure will be this pi bond remains intact, the pi bond comes here, bond is broken from this carbon, so positive charge will be on that carbon atom, the substituent present Y, above the plane electrophile, and below the plane the hydrogen. So these three are the resonating structures if the electrophile comes in ortho position. Okay, now let's see what happens if the electrophile comes in meta position, and we have to do those resonating structures also. Okay, let's see what happens. Now if electrophile comes in meta position, the Y substituent already present, the pi bonds are here, that is the electrophile. Now if electrophile comes in meta position, that's here, so the pi bond will be broken from this carbon and will make a bond with this electrophile. Okay, so the carbocation formed will be, electrophile will go in these positions in above the plane, and the hydrogen will go to the below the plane. The hydrogen which was already present in the benzene ring will be in the below the plane. These two groups cannot lie on the same plane. Okay, in this process the planarity of the benzene is lost. Okay, all those carbon atoms of benzene are sp2 hybridized, that is all carbon atoms are planar, and these hydrogen atoms are also in the same plane. But when a group is there, two groups, that is the electrophile and the hydrogen, which are attached with the same carbon for a time being, cannot be on the same plane because there will be a chance of steric hindrance. To avoid that steric hindrance, the electrophile goes into the above positions and the hydrogen in the below, above plane and the below the plane. Okay, that's why we are writing here in this manner. Now the bond is broken from this carbon, so the positive charge will be there on this carbon atom. These two pi bonds remain intact. Now what will be the resonating structures of this carbocation? Just to reduce the positive charge, this pi bond will come here and the bond is broken from this carbon. So in the next resonating structure, this carbon will carry a positive charge. So the next resonating structure is like that. Here the substituent Y is present, these pi bonds remain intact, the electrophile is above the plane, the hydrogen is below the plane, the bond comes here to double bond, and the bond is broken from this carbon. So in this resonating structure, this carbon will carry a positive charge. Now to shift that positive, now to reduce that positive charge, this pi bond will come here. Okay, so pi bond comes here to make a double bond, and the next resonating structure is benzene, the hexagonal structure. Here Y, here above the plane electrophile, below the plane hydrogen. This bond remains intact, and this bond comes between these two carbon atoms, so a positive charge. Since the bond is broken from this carbon, so this carbon in this resonating structure, this carbon will carry a positive charge. So these are the resonating structures if the electrophile comes in meta positions. Now let's see what will be the resonating structures of the carbocation when the electrophile comes in para position. Okay, let's see. Here is the benzene which is carrying a substituent Y, and we are giving electrophile E plus. Now if this bond, if electrophile comes in this para position, so the bond, this pi bond will be broken from this carbon and will make a bond with the electrophile. Okay, So the resonating, so the structure of the carbocation is these two bonds remain intact, the electrophile comes above the plane, and the hydrogen already present there will be in the below the plane positions. Bond is broken from this carbon, so this carbon will carry a positive charge. Okay, next what happens here, the resonating structure. The aim of resonating structures, why resonating structures is formed, just to, the aim is just to reduce or just to neutralize the positive charge. So how can they neutralize this positive charge of this carbon? If that pi bond shifts from here to there, then the bond breaks from this carbon and make a bond between these two carbon. So the resonating structure is like that. This bond remains intact. Here Y already present, electrophile in above the plane positions and below the plane hydrogen, and here a bond was already there. This bond remains intact, and positive charge is here because the bond is broken from this carbon, and a positive and a double bond is also formed. Sorry, double bond is formed here. Okay, so in the resonating structures we can see, if the electrophile comes in ortho and para positions, then two resonating structures are formed. Here we can also make another resonating structure if this pi bond goes there. So the next resonating structure is benzene, electrophile, this bond remains intact, bond comes here and the positive charge is carried by this carbon, electrophile is above the plane and below the plane there will be a hydrogen atom. So in ortho positions the resonating structures are there, in meta positions the resonating structures are here, and in ortho positions the resonating structures. So we have drawn all the resonating structures. Okay, now let us consider the relative stabilities of those resonating structures. Look, if the electrophile comes in ortho positions or para positions, then a particular resonating structures are formed here in ortho position and here in para positions. In these two resonating structures, the carbon which is carrying the positive charge, the carbon is which is carrying the positive charge has already a substituent. Okay, look here, in this resonating structure and in this resonating structure, the substituent bearing carbon is carrying a positive charge, but no such resonating structures are there in case of meta substitution. No such positive charge is there, that is Y bearing carbon is not carrying any positive charge. Now think, if Y, the substituent, the already substituent present Y has a plus I inductive effect, that is electron donating effect or electron repelling effect, then that substituent will stabilize these two resonating structures by pushing the bond paired electrons towards the carbon which is having a positive charge. Okay, now if Y has plus I inductive effect, these two resonating structures will have some greater or some extra stability. As the Y has plus I inductive effect, it will push or repel the bond pair electrons towards the carbon which is carrying the positive charge, and will make these two particular resonating structures more stable. Okay, but in case of meta orientation we are not, in case of meta substitution we have not any such resonating structures where this carbon is having a positive charge. Okay, so if Y has, the already substituent present Y has plus I inductive effect, then Y will stabilize these two resonating structures. So the substituent will add on ortho and para position just to have some extra stability, because in meta positions no such extra stability is there. So the conclusion is that if the substituent has a plus I inductive effect, then that substituent must be ortho-para orienting. Okay, that is why since CH3 group has plus I inductive effect, that is why in the electrophilic substitution of toluene we get a mixture of ortho and para nitrotoluene, because the substituent, I am telling you again, if the substituent already present in the benzene ring, then if that substituent has plus I inductive effect, then that substituent is ortho-para orienting or ortho-para directing. Now in case of meta orientation, no such extra stability is present. That's why in case of a substituent which has plus I inductive effect, no meta orientation will be there. But if the substituent has minus I inductive effect, that is electron withdrawing effect, then these two resonating structures will be highly unstable, as it is carrying a positive charge, and if Y is withdrawing electrons from a carbon which is already having a positive charge, that will make it very unstable. That's why if Y has minus I inductive effect, then it will not be meta orienting. That incoming electrophile will not go in the meta position, because if it goes to the meta position, then those two, if Y has minus A inductive effect, then it will be meta orienting, because in ortho-para orientation we are having those two resonating structures where the carbon which is carrying the substituent is having a positive charge. If Y has minus I inductive effect, then it will destabilize these two resonating structures. That is why if Y has minus I inductive effect, then the incoming electrophile will not come in ortho and para positions. It will be in meta position where those extra instability is not there. Okay, so the conclusion is that if Y has plus I inductive effect, then it is ortho-para orienting, and if Y has minus I inductive effect, then it is meta orienting. Since CH3 group has plus I inductive effect, therefore in presence of CH3, that is in toluene, the incoming electrophile NO2 plus comes in ortho and para position, but NO2 group has minus I inductive effect. That is why if in the electrophilic substitution of nitrobenzene, the incoming electrophile nitronium ion, which is produced in the reaction mixture of a mixture of concentrated nitric acid and sulfuric acid, the NO2 plus is the generated electrophile that comes in meta positions, because NO2 has minus I inductive effect. That is why it is meta orienting, and since C3 has plus I inductive effect, so it is ortho-para orienting. So that is the conclusion. Okay, you have to remember that if the substituent present has plus I inductive effect, then in the electrophilic substitution reaction, a mixture of ortho and para isomers will be formed. That is, the incoming electrophile will go in ortho and para position separately, and if Y has minus I inductive effect, then the incoming electrophile go in the meta positions. Okay, now there are some extra questions also. What happens in the nitration of phenol? That is, in phenol, if we give a mixture of concentrated nitric acid and sulfuric acid and maintain a temperature of 50 to 60 degrees centigrade, then what happens? Let's see. Okay, now let's see what happens when phenol is treated with a mixture of concentrated nitric acid and sulfuric acid at a temperature of 50 to 60 degree centigrade. Previously, in the previous video, I have seen you the reaction mechanism of nitration of benzene in the reaction mixture of nitric acid and sulfuric acid. Actually, what happens, the nitronium ion is formed. How? that is a OHNO2. We can write HNO through HNO3, that is nitric acid, in this manner, and here sulfuric acid is also added. So sulfuric acid being an acid will release H plus ion. So H plus ion that comes from sulfuric acid, H2SO4, and this oxygen has a lone pair electron, and H plus, remember H plus is also called a proton. Why it is called a proton? Hydrogen, a normal hydrogen atom has one electron and one proton, and no neutron is there. Okay, now if you remove that electron, then H plus ion is formed, which is only a proton and nothing else. That's why H plus ion is also called a proton. And in H plus, and in hydrogen atom, only one electron is present, and that is 1s1. Now if you remove that electron, H plus ion is formed where no electron is present. So the 1s orbital is completely vacant. So if someone give its lone pair electron to H plus ion, the H plus can accept that lone pair electron and can accommodate that lone pair electron in its vacant 1s orbital. So H plus ion is a Lewis acid. Lewis acid is that which can accept lone pair electron, and the Lewis base is that which can donate lone pair electron. So here oxygen has a lone pair electron, so it can donate the lone pair electron to H plus and make a coordinate bond with the H plus ion. So here a coordinate bond is formed. So HO becomes H2O, and the NO2 is still bonded with this. Since oxygen is giving up its lone pair electron, a positive charge is there in oxygen atom. Now here neutral H2O is removed by having this bond pair electrons. Okay, so here neutral H2 is released, and NO2, the bond is broken, so N will have a positive charge. So NO2 plus ion is formed, that is called nitronium ion, and this is the generated electrophile in the nitration reaction of benzene. Okay, now what happens, this pi electrons attached to or attached to that NO2 plus ion, and the NO2 is bonded with benzene. That is how substitution of nitration occurs. Now what happens if in the substitution of phenol, the nitro group NO2 plus ion actually comes in all the three positions, that is in ortho, in para, and in ortho dash at once. Okay, so at the same time all the three NO2 groups attached to phenol. So phenol, why this happens? Let's see why this happens. In phenol, oxygen has a lone pair electron. Okay, oxygen has a lone pair electron, and that lone pair can easily get delocalized into the benzene ring through resonance. How? Oxygen make a pi bond with, or make a double bond here. Carbon have five bonds, which cannot be possible, so that one of the pi bond has to be broken, and this pi bond shifts on this carbon atom and giving it a negative charge. So the resonating structures of phenol is like that. Here a double bond is formed, OH. Oxygen is losing the lone pair electrons to this carbon, so oxygen will have a positive charge. These two bonds, pi bonds, remain intact, and the pi bond shifts here as a negative charge. So this one is the resonating structures of phenols. The next resonating, what will be the next resonating structures? This negative charge is also in conjugation of the pi bond. Conjugation means alternative. Okay, so the negative charge can be make a double bond, and the pi bond will be shifted in the form of negative charge. So the next resonating structure is like that. OH, oxygen will carry a positive charge, here double bond, and here a negative charge. Okay, the next resonating structures, what will happen? The next resonating structure, negative charge will make a double bond with this carbon, and this pi bond will be shifted on the carbon. So the next resonating structure is that double bond OH, positive charge, here negative charge, double bond. Okay, so these three are the resonating structures of phenol. Now you can see, now what is resonance? Resonance is the difference form where a molecule can exist. Say we all have different forms. When I'm teaching you. I'm a teacher. When I go to school, uh, I'm a school teacher. When I am at my home, then I am someone's father, someone's husband. So and I'm also someone's friend. So I have some different forms and I exist with all of these forms. Every person has some different forms and they are the mixture of all those forms. One cannot identify a single person with a single form. They have different forms. So molecules also have some different forms and they exist having with all those forms. So phenol exist in all these resonating structures. Where there is a phenol, all the resonating structures must be there. Okay, so here we can see in ortho, para and in ortho dash, these three positions a negative charge is concentrated. Okay, so when NO2 plus is there in the reaction medium, NO2 plus will be bonded with all those positions at once. That's why in case of nitration of phenol, a mixture of in case of the nitration of phenol 2,4,6 trinitrophenol is formed, which is also called a picric acid, which is also named as picric acid. Okay, now someone asked me what is boiling point. Okay, let's answer, though it is related with the topic. Let's answer. The boiling point is the temperature at which a compound starts to boil and the temperature remains constant until all the solution is boiled off. Okay, someone asked me a question, sir, what is boiling point? Though it is not related with today's topic, but as he asked me, so I am answering you. The boiling point is the temperature at which solution starts to boil and the temperature remains constant until all the solution is boiled off. That is, the temperature of water is 100 degrees centigrade at 1 atmospheric pressure. So at 1 atmospheric pressure at 100 degrees centigrade, water will start to boil and it will be, and the temperature, if you put a thermometer into the solution, you will have 100 degrees centigrade and it will remain constant until all the water is boiled off. That is a question from a solution. We'll have a video, we'll have a live streaming on that topic also. Okay, so for today, this is in case of aniline. Aniline, you see what is aniline, you know, benzene and NH2. Now you know nitrogen has also a lone pair electron, and that lone pair electron can also get delocalized into the benzene ring, giving a rise of some resonating structures. So aniline, in case of aniline, the same thing happens. Okay, so the resonating structures of aniline is double bond NH2 and carries a positive charge, and it has given up its lone pair electrons. So a negative charge is here, double bond. So the next resonating, what will be the next resonating structure? Double bond, negative charge. So NH2 plus double bond, negative charge, and what will be the next resonating structure? Double bond, negative charge. So this is the next negative charge, double bond, NH2 plus. Now you are also, you can see that ortho, para and ortho dash, in these three positions, a negative charge is concentrated. So in the electrophilic substitution of aniline, a 2,4,6 compound is also formed, that is if you nitrate aniline by giving a mixture of nitric acid and sulfuric acid at a temperature of 50 to 60 degrees centigrade, then R246 trinitroaniline is formed. Again, in the bromination of aniline or in the bromination of phenol, if bromine water is added in phenol or aniline, 2,4,6 tribromoaniline or 2,4,6 tribromophenol is formed. Okay, so that's all for today, and the next day we'll have some physical chemistry. Okay, bye bye.